All right, everybody. Let's finish up what we need to finish up from the other day, and then we'll get started on the problems that we need to work on for today. So, we've been talking about organometallic reagents and the fact that they can make alcohols. What two organometallic reagents have we focused on?
The one with aluminum.
Pardon? That's not an organometallic. That's a hydride reagent, but what's an organometallic reagent? Okay.
And chromium.
Chromium? Yeah. We didn't talk about chromium. So what were the names of the two that we talked about? The one with magnesium is called a what reagent? That's a Grignard reagent, right? How do we make a Grignard reagent? That's right. We need some sort of alkyl or aryl halide, and we need magnesium metal. What reaction conditions do we need? What kind of solvent can we use? Not ethanol. We can use diethyl ether. The ethers are typically used for making Grignards. Alkyl lithiums. How do we make alkyl lithiums? And how much lithium? I need 2 moles of lithium for every mole of alkyl halide. We can make those in ether if we're going to use them quickly, but for long-term storage, we cannot because they do react, and you end up having the alkyl lithium function as a base on the ether with the elimination of an alkoxide. And so that reaction is slow, so if you're going to do the chemistry quickly, it's fine to generate them in ether, but if you're going to make them and try to store them, you typically need to use something like a pure hydrocarbon like hexane or pentane or something like that. All right, so when we react an organometallic reagent with aldehydes and ketones, ultimately we get alcohols. Okay? If I take a ketone or an aldehyde and I react it with an organometallic reagent like a Grignard or an alkyl lithium, I'm going to get some type of alcohol. And depending on what kind of carbonyl compound that is going to dictate what kind of alcohol I get. So for example, here we have a methyl Grignard. We're going to react that with formaldehyde. Formaldehyde has no carbon bonds in it until we react it with the Grignard reagent. Okay? And so upon workup, we get a primary alcohol. So if I want to make a primary alcohol using a Grignard reagent, I need to use formaldehyde. Okay? And it works quite well, actually. Okay? What do we call this intermediate? It is the tetrahedral intermediate, right? If I take an aldehyde that has already a carbon-carbon bond and I react it with an organometallic reagent, here they're picking on the lithium reagents, right? Notice now I have 2 carbon-carbon bonds to the carbonyl, what was the carbonyl carbon in the tetrahedral intermediate. And so when I work this up, I end up with a secondary alcohol. If I take a ketone and I react it with an organometallic reagent, here we're using a lithium alkanide. Now we formed an additional carbon-carbon bond, and after workup I end up with tertiary alcohols. So we can make primary, secondary, or tertiary alcohols from Grignard reagents depending on what type of aldehyde or ketone we use. Okay? So again, this is you have a lot of ways to make alcohols now. You can add Grignards and alkyl lithiums to carbonyl compounds. You can add water across carbon-carbon double bonds. You can do hydroboration oxidation. You can do oxymercuration demercuration. Lots of ways to make an alcohol. Okay? And each of these methods has its own advantages. Okay? The cool thing about this one is that this allows us to make new carbon-carbon bonds. Okay, so we're making carbon-carbon bonds while we're making these alcohols. So it's an important step in a variety of syntheses is to add a Grignard or an alkyl lithium to a carbonyl-containing compound. Okay? We can also react Grignards and alkyl lithiums for that matter, although here we're just looking at Grignards. We can react these with carbon dioxide, and ultimately we can make carboxylic acids. How do we know right now to make carboxylic acids minus this procedure? Technically, yes, but we would start from something prior to the aldehyde. Pardon? Jones reagent. So primary alcohol plus Jones reagent gives us a carboxylic acid. Now, technically, Jack is right. That is the further oxidation of the aldehyde that gets along those ways, along that way. But anyway, we can oxidize primary alcohols. What else have we learned to make carboxylic acids? From last semester. Carbon-carbon triple bonds. What? Ozonolysis of a carbon-carbon triple bond, right? We can make a carboxylic acid. But we can also make carboxylic acids by the reaction of a Grignard with carbon dioxide. So for example, here we're starting off with chlorobenzene, reacting it with magnesium to make the Grignard reagent. Then we take this and place it in solution with carbon dioxide. Let that reaction go to completion, and then we react that or work that up with just some dilute acid, and we can get the new carbon-carbon bond. So what's the mechanism for this? What does carbon dioxide look like? Not quite. Bent? What's the structure? What's it look like? How would I draw it on the board? Well, let's start with the carbon. Where are the oxygens? And? Is that carbon dioxide? Not yet. What do we have to do? I have to have two double bonds, right? What's the hybridization of carbon and carbon dioxide? It's sp, right? However, if I look at just half of this, it looks like a carbonyl compound, right? It's just not sp2 hybridized. So if I have a Grignard reagent, what's it going to do? If it attacks that carbon, what happens? It's going to break one of the weak pi bonds, right? Either one, doesn't matter. They're the same. And that's what you get. Grignard reagents do not add to carboxylates because this negative charge forbids the negative charge of the Grignard from approaching too easily. Okay, lithium reagent's a little different story. But nonetheless, it stops here. That sits in solution until we dump it over acid, and the oxygen then gets protonated and becomes the carboxylic acid. Okay? It's a very easy way of making carboxylic acids, actually, is to do this. Technically, it's a little challenging. How do we get carbon dioxide into a reaction? It's a gas. So you got to bubble it through the reaction. And it's got to be dry. So you got to dry it before it goes through the reaction, because we know if there's moisture around, it'll react with the Grignard, right? So we got to avoid that. So you got to deal with piping and regulators and tanks of carbon dioxide. You can use dry ice, but dry ice is even a little more challenging because it's so cold that water freezes on the outside of it, and so when you try to throw it into the solution, there's a lot of water around. So the easiest way to, or the most practical way to do it is to bubble dry carbon dioxide gas through it. If you look at examples like this, so this is a synthesis example. So how would we make phenylethanol, which is this product right here, from a Grignard reagent? Okay, or so from bromobenzene. Well, if we look at it, we know that the bromobenzene has to give us the benzene part, right? And we've got a new carbon-carbon bond. And the easiest way to do that, of course, is to take bromobenzene and convert it into a Grignard reagent. But in looking at this, we notice that we have 2 additional carbons that we need. One of the easiest ways to get those 2 carbons is to react the phenyl, 'phenyl- 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 It's an epoxide with the two carbons that we need, right? What's going to happen? What happens? How would I push the arrows? How do we push the arrows, Ahmed?
Well, the oxygen, the one paired with oxygen will go somewhere.
Nope.
No.
What is a Grignard? Is it a nucleophile or an electrophile? It's a nucleophile. What do nucleophiles do with epoxides? They ring open them, right? So how would I push the electrons? Right here? And what would I do with it? Attack the ring where? At either carbon, right? Breaking open that and giving me an alkoxide, which then gets protonated on workup to give me this alcohol, right? So what kind of alcohol did I just make? Primary alcohol, right? How do I take a primary alcohol to an aldehyde? What do I have to do? I have to oxidize it. Can I just use any oxidizing agent? What oxidizing agent do I need to use here? That's a reducing agent. PCC. PCC is the one you want to use here. PCC and dichloromethane will oxidize the primary alcohol to the aldehyde, and it stops there, right? And you end up with that aldehyde. So you can actually synthesize these types of things from Grignard reagents, knowing what kind of electrophiles you need to react them with, okay? There are some limitations of Grignard reagents and alkyl lithiums. We're going to focus on Grignards. We know that a Grignard reagent has a pKa of somewhere around 35, 40, something like that, okay? And so if a molecule has any hydrogen atom in it that has a pKa less than that Grignard reagent is going to react with that proton, okay? It's not going to add to your carbonyl because we know that acid-base reactions occur faster than addition reactions, okay? So, for example, if we take an alkyl Grignard, we react it with some type of acid, right? As long as this pKa is less than 35, this reaction pretty much is going to lie to the right. And this is going to put a proton on our molecule, okay? Now, if that's what you want to happen, great. But quite frequently, this isn't what we want to happen, okay? And so if your molecule contains things like alcohols, amines, either primary, secondary, if it contains carboxylic acid, sulfonic acids, thiols, or alkynes that are terminal with a hydrogen, you're going to run into problems with using Grignards. And what you're going to have to do is find ways in which you can protect these functional groups so that you can do the chemistry that you want to do. What is a protecting group? What does a protecting group do for us? Okay, temporarily blocks the functional group, right? What kind of criteria are there for a good protecting group? Has to be easy to come on, has to be easy to come off, but it needs to be stable to the reaction conditions you're doing, right? So in this case, you would want something that you could put on easy. You could do the chemistry with a Grignard, and a Grignard's a pretty good base, so you want a protecting group that's going to be stable to base. And then at the end, you want it to be able to come off pretty easy, probably by dumping it into acid, right? Because it needs to be stable to base, so we'll probably want something that'll come off pretty easily in acid, okay? And so we call these groups protecting groups. And like I mentioned earlier, there's a book this thick in my office that is nothing but page after page after page after page after page of protecting groups. There's entire graduate courses designed just to cover protecting group chemistry, okay? So last time when we talked about protecting groups, we talked about T-butyl ethers. We could form a T-butyl ether from an alcohol, and we also talked about silyl ethers, right? Here's another one for you. It's called the trittle group. Okay? And so if you look at it, it kind of looks like a T-butyl group, except it's got 3 aromatic rings instead of 3 methyl groups around it. So if you take this alcohol and you react it with trittle chloride in the presence of pyridine, you will make a trittle ether. And it turns out that trittle comes off very, very easily in acid and a little bit of water. Okay? So a lot of people like to use it. And the reason it comes off so easy, it actually comes off easier than the tert-butyl one. Because if you think about a carbocation at this carbon, it's extremely stable because of all the resonance structures you can draw for it. So what we want to do in the chemistry, right, is we want to react this carbonyl with some Grignard reagent, make a new carbon-carbon bond here. But if we just took this Grignard reagent and put it in with this unprotected, this Grignard reagent would simply react with the alcohol and not give us the product we want. So what we have to do is protect this. We're going to protect it as an ether called a trittle ether. We've put on the trittle group. We no longer have the OH bond, so there's no longer an acidic hydrogen to worry about. We isolate this, purify it, whatever we need to do. Then we react it with our Grignard reagent. We make the carbon-carbon bond that we want to make, and we go through the tetrahedral intermediate. Then we simply dump this into aqueous acid. They put a little bit of ethanol around just to make everything soluble, and lo and behold, you protonate this, right? And you also remove the trittle protecting group, all in one step. So it's easy to come on, easy to come off, protects the chemistry, or protects the functional group that we don't want to interfere with the chemistry that we are doing. This is where Mother Nature does chemistry so much better than we do. We are still trying to mimic Mother Nature in how she does her chemistry, because she doesn't use protecting groups. She uses enzymes, and enzymes have a way of excluding the functional groups away from the site of reaction. Okay? So that's all we needed to talk about today. We've got an inverted lecture, the rest of the material.